So my presentation focus on vineyard scenario generation and optimal control for automated operation in virtual environment. And we will face these different aspects such as vehicle dynamics, environment, and in-field sensors according to the last precision farming technology. So let's start with the outlines of my presentation. So first of all, we will see the target and motivation, so why this kind of project has been developed. Then we will see the vineyard scenario generation procedure, the autonomous driving logic we develop, plant inspection logic, and at the end, the conclusion. So let's start from targets and motivation. We can say that a global food problem exists. Okay, this is the situation today of the population in the world. So we are 8 billion people, and we are divided more or less 45% in countries and 55% in cities. This is the forecast situation for 2050. So we will be 11 billions, and most of these 3 additional billions of people will live in city. This for sure leads to some problems. We will have 3 billion more mouths to feed, which leads to 50% in increase of food demand. The depopulation of rural areas leads to fewer agricultural workers, and we have also to take into account sustainability problems, which leads the governments to impose a reduction in the utilization of water, fertilizers, pesticides, and so on. So for sure is a challenging scenario for the future, and to face it, farm innovation is mandatory. And one of the aspects of this farm innovation is precision farming. Here you can find a possible definition. There are many definitions of precision farming. This is one of the possible definitions. So it's a farming management strategy based on observing, measuring, and responding to temporal and spatial variability of the soil to improve agricultural production and sustainability. So, precision agriculture, precision farming is a wide range of technologies and management methods. But if you apply it to viticulture, as in our case, we can find, for example, this kind of systems. So, a trajectory calculation, autonomous driving, plant inspections, implement actuation, and so on. All these systems aim to reduce the labor cost, improve the crop health, and enhance the productivity. The question is, okay, there are very cool systems, but how to develop and test this kind of systems? We have 2 ways that are the usual 2 ways that we have always when we talk about development and testing. The first is experimental and simulation. I don't want to enter into detail of pros and cons of experimental and simulation in general for automotive field. We already know them. But I want to focus more on this kind of particular field, so agriculture and vineyard operation. So if we start from experimental, we can see some critical points. Experimental in this case is season and weather dependent. So I cannot do all the agricultural operation that I want in every moment of the year. It's not possible. So it's season dependent. I have an impact of production in case the test fail. I can have an impact on production. Sometimes the tests are not repeatable. For example, if I have to test a distribution logic for an atomizer, and I want to test 2 different sets of parameters of my logic, I do the first test, but during the test I spray something on the leaves of the plants. And so then I cannot remove what I sprayed before to repeat again the test. It's impossible. I can do it on another vineyard, but it's not the same vineyard. So I introduce other variables, and it is not good for, let's say, understanding the system, the problem of the system. There is a difficult replication of edge situation because I cannot control them. For example, fog, presence of animals, presence of particular obstacles, and so on. And there is also a safety risk. If I have to test in dangerous conditions, for example, with particular high slopes and so on, it becomes very risky for the operator. Take into account that overturning is one of the most accidents that occur in agricultural field, so it's very dangerous. So we don't like this way so much, let's say, and we can say that it's good only for the last mile of development. For simulation, instead, we can have the same, let's say, list of points, but with, let's say, a positive meaning. So season and weather independent, no impact on production, also always repeatable, easy replication of edge situation, no safety risk. So we like this path, but to simulate in Vineyard, we need a reliable simulation platform capable of replicating a Vineyard scenario. And this platform should include all these aspects, so tractor and robot vehicle, or robot vehicle model, georeferenced real field, realistic field morphology, soil irregularity, interaction with plastic soil, and then the presence of the rows of vines and different maturity level of the plants. The first 5 points are already included in already existing solution that is called Agrisy, that is a product from SI. It's a simulation platform to simulate the vehicle dynamics for agricultural vehicle and the precision farming systems, and works in collaboration with car maker and truck maker. The last 2 points instead are new, and we need to develop them. So the main target of this work is to develop a robust virtual environment where we can simulate and optimize autonomous operations in vineyards. And then to demonstrate the effectiveness of this environment, we will use it to develop 2 prototype control logics, one for autonomous driving and one for plant inspection. So let's start to see how it is possible to automatically generate a Vineyard scenario to be used for simulations. To start this process, we need some ingredients. And these ingredients is taken from a common GIS software. In this case, we use QGIS, that is a GIS software that is open source, free and open source, which permits to identify the field, every field in the world that we want to, let's say, replicate in simulation. And it permits to play a little bit with the satellite images to extract this kind of file that are called shape files. The orange one is a shape file which describes the boundary of the field. The blue one is a shape file which describes the position of one vines row. So these are the ingredients that we need. Once we have them, we can start the procedure of generating the scenario. We can divide it into steps. The first step is already existent, let's say, and exploit a tool that is called Agrisy Scenario Generator that, starting from the shapefile of the field boundary, generates an RD5 file of the field to be loaded in CarMaker. This RD5 file is georeferenced, contains a drivable area with a soil texture, a boundary of the field with a dirt road texture, and realistic elevation profile. This is an example of the output of this, let's say, automatic routine. But we don't want this. We want a vineyard, so we have to add something. And now we have the second phase of the procedure that starts from the previous obtained RD5 file of the field and from the shape file of the vine row that we obtained before from the GIS software. We develop a new tool that is called Vineyard generation, which asks some parameters from the users and is able to generate a new RD5 file of the vineyard, in this case, which has the same characteristic of the previous one, plus the presence of rows of vine plants with defined maturity level. What do I mean with maturity level? From, let's say, the scenario point of view, is just a different graphical object that we can use for the vineyard. In particular, we have 3 different maturity levels: low, medium, and high. So this was the result from the previous, the first, let's say, step of generation. With the second step, we can obtain something like this. So we had the rows of plants on the field with different maturity level. This is an example of how the scenario, the vineyard appear inside the Agrisys simulation. Okay, so now we can generate vineyards and use them in simulation. What we want to do is to demonstrate that this scenario is useful to develop something. And in particular, as first, let's say, use case, we try to develop a prototype autonomous driving logic to drive the tractor or the robot, in our case it's a tractor, inside the vineyard in autonomous way. So for this part, we will see methodology, results, and then we will do also some sensitivity analysis on some parameters, surface irregularities and adherence conditions. So let's start from the methodology. We consider a simple scenario, not the big vineyard of before, but a simpler scenario to be used as a logic development testing ground. The rows of plant are not straight, but has a slight curvature to face, let's say, a more critical situation. And we have different vegetative conditions, so different bounding boxes of the plants. On the right graph, you can see a bird's eye view of the bounding box of the vineyard that we built. We can divide the problem in 2 parts, okay? In 2 phases. We have the straight phase and the U-turn phase. In the straight phase, we have the tractor that is in a corridor between 2 rows of plants. Go at constant speed. We need rows of plants detection, and we want to create a steering control able to maintain the tractor in the center of the corridor. The U-turn phase, instead, we have the tractor which reached the end of the field, so we need a speed regulation. We need to know the minimum turning radius of the tractor, and we need a steering and longitudinal control which permits to exit from one corridor and enter in the next one. So let's start from the methodology of the first phase, the straight phase. We need a sensor that is able to detect the distance between the vehicle and the left and right rows of plants. In this case, we make the hypothesis of ideal sensor. Okay, so once the vehicle is inside the corridor, the relative position between the tractor and the plants is known and accurate. Okay, we don't consider the error of the sensor. The signal coming from the sensor enter inside a steering control that is an MPC controller that follows a trajectory that is a sensor-based trajectory built using the signal coming from the sensors. For the second phase, so the U-turn phase, instead, we have again a sensor, but the sensor in this case works only like a trigger to detect the exiting from a corridor of vines. We need some information from the vehicle, the minimum turning radius, and from the scenario, the plant rows distance. Also in this case, we have an MPC controller, which permits the tractor to follow a predefined trajectory. And this trajectory is built in this way. So we try to connect the plant rows distance with the minimum diameter, turning diameter of the tractor with a drivable path. If we see some results of this method, so here we can see a comparison between the trajectory followed by the tractor using the MPC controller in green and, let's say, the optimal trajectory to maintain always the tractor in the middle of the corridor in yellow. Here we can see a zoom of the two U-turn phases with the indication of starting and ending point of the phase. And here instead a zoom of some parts of the straight phases. In the right graph is highlighted the error that the tractor do when enter for the first time inside the vineyard. Just to have a summary index, the RMS of the lateral error of the trajectory is reported in this graph. We can see the numbers, and we can see that, for example, in the first rate, we have a higher error that is due to that, let's say, entering phase that we see before. If we make some sensitivity on surface irregularities, we can, let's say, introduce a bump wave irregularities with a 60 degrees of inclination with respect to the horizontal axis, a period of 1 meter, and a height that vary from 25 to 65 millimeters. We repeat the test with different level of irregularity, and this is what we obtain. So we can see that the control logic is sensitive to the irregularity because increasing the level of irregularity, also the lateral deviation increase in all the phases of the control, straight and U-turn. For what concerns instead adherence condition, in this case we try to repeat the test with two different levels of potential friction of the soil. In this case we can see that the algorithm, the system is not so affected by adherence as there are very slight difference in lateral deviation. So we can see that friction coefficient doesn't affect the control logic in this case. The second logic that we try to develop starting from our vineyard scenario is a plant inspection logic. Also in this case we will see methodology and some results. Okay. We consider a simple scenario built starting from a real vineyard, and we consider only a subset of this vineyard. And we create different vegetative conditions randomly distributing 3 different levels along the field. So you have 3 different levels of maturity that are positioned on the field randomly. To obtain the data, we use the same sensor we see before with the same hypothesis of ideal sensor. And in this case, the algorithm is divided into 2 phases. We have an online phase in which the tractor drives inside the vineyard, scan the vineyard and collect the data. And then there is the second phase, which is a post-processing phase, in which the data are analyzed to obtain a final vegetative state map. Let's see some results. So this is an example of the signal detected by the sensors. We have left and right signal in light and dark blue. On the right side, on the left side is printed against the travel distance. On the left side, instead, we have a bird's eye view of the same information. This is a comparison between what is seen by the sensors and the actual bounding box of the vineyard in red. And here we can see the final result. So the algorithm is able to detect 3 different vegetative state and to assign one level to each part of the vineyard. So we have in yellow vegetative maturity level 0, that is the lowest. In orange, medium vegetative level, that is level 1. And in red, higher vegetative level, that is level 2. Again, to have a summary evaluation index of this kind of algorithm, we can calculate the percentage of detection for each level. So does it mean that if I have 100 points on the vineyard that has maturity level equal to 0, I'm able to detect only 79. If I have 100 points of maturity level 2 in the vineyards, the algorithm finds out 116 points, so more than the points that are actually present. So we can say that the algorithm tends to overestimate the maturity level. And this can due to this blind zone that is reported with the yellow region in the figure that occur when I pass from a higher maturity level to a lower maturity level, and the sensor is not able to detect that part of vineyard. So it continues to say high level for a certain distance before to pass to the lowest level. So, just to conclude, an algorithm has been developed to generate a georeferencing scenario that replicates an existing vineyard, starting from data obtainable from common GIS software. The scenario file is automatically generated for import into Agrisy, and so car maker or truck maker simulations. The effectiveness of using a generated vineyard scenario for the development of control logic has been demonstrated. As example, the setup of 2 prototype algorithms has been shown. The first was an MPC controller for autonomous driving within the vineyard, and the second was an automatic evaluation of the maturity level of the plants. So, thank you for your attention. If you have questions, you can ask. Thank you.